Okay, let's get started. The next major unit of the textbook of the Luenberger book is chapter 3 on Hilbert spaces, and its immediate sequel in chapter 5, which is on dual spaces. These chapters are tough. And in these chapters, we will extensively use concepts like the maximum and minimum, or supremum and infimum of functions, which are related concepts, but we need to be able to draw sharp distinctions between these concepts. So we shouldn't confuse minimum and infimum on the one hand and maximum and supremum on the other hand. So before turning to chapter 3, I thought it would be useful to revise our command in basic concepts like minimum, maximum, and the like, etc., etc. So in this lecture, which is an applied session, we will go into problems from basic functional analysis to practice how to distinguish between minimum and maximum, etc., as I have just mentioned. So we will work out detailed solutions to 3 problems in turn, and to begin with, let's turn to problem 1, which is about a series of functions in which we are supposed to find the maximum or the supremum. So to solve this problem, to work out the solutions, we are supposed to be certain about the distinction between maximum and supremum. And this problem is designed to shed light on this distinction. So let's turn to the problems. Okay, so let's go over the problems, the sub-problems, one by one. In problem A, we have the following function, 2x minus 1, and most importantly, the domain of the function is an open interval. So over such an open interval, there is no maximum, only supremum, because working on an open domain, we can get arbitrarily close to 1. This is the value that the function takes at the upper end of the domain. So because of, once again, because of the open interval, there is no maximum, but only a supremum, which is 1. So this is the first warm-up exercise. In problem B, we have a quadratic function with the leading coefficient as a negative number. So the leading coefficient is negative, and the domain is unrestricted. So we work on the whole real line. So at the end of the day, this is a simple, unconstrained optimization problem to find the minimum, to find the maximum because of the negative leading coefficient. We have a maximum. To find the maximum, we need to have the first differential, which equals to 0, and on this basis the function takes its maximum at 0. So the maximum of the function is 3. Note that we use the basic fact that the leading coefficient is negative, so this is a reversed parabolic function, and obviously it has a maximum. In problem C, we have a basic periodic function sinus x, and the domain is the whole real line. So this is a periodic function which takes its maximum periodically. I know you are all familiar with the graph of the sinus function. Pi over 2 pi. So we can scale the horizontal axis very easily. Three pi's, and at this point, so we start at the origin, in the origin actually, and we have this fancy wave. I'm terrible at drawing, as you can see, and these are the maximum points. So in sum, we can say that the maximum of the function is 1, and the places of maxima are easy to identify because we can count them. Okay, in problem D, we have another periodic function which is a special distorted sinus function which is divergent. So given that the domain is still unrestricted, over this domain the function is divergent, so it tends towards infinity. In this case, there is neither a maximum nor a supremum. There is no such a thing as least upper bound. So we have no maximum, we have no supremum, there is no such thing as least upper bound. This is divergent. Okay, in problem E, we have another familiar function, 1 over x, and the domain is still the whole real line. This is similar to the previous case. If x is approaching 0 from above, then fx is approaching infinity, and on the other hand, if x is approaching 0 from below, then fx is tending towards minus infinity. So again, we have a divergent function, so there is no such a thing as the supremum of f. So in short, we can say that the supremum of fx, d and e standing for doesn't exist. All right, F. Problem F. It's really beautiful because our function consists of two parts. supposing that the domain is the union of two open intervals. So this is a nice exercise, and we might try to draw a simple figure. Okay, so this is the domain. We have holes over the domain. This is 1, this is 2, and the function is interpreted only over the blue lines, and at the holes we have no value for the function. This is 1. So the function looks like this. No, I like to use green. This is supposed to be a straight line. Okay, and the other section of the function is somewhere here, starts somewhere here. This is another straight line. So this is the function. This is another special case. The function has neither a maximum nor a minimum, but it certainly has a supremum, which is 1. Okay. Problem G. This is a quadratic function with a positive leading coefficient. So this is a standard parabolic function, and the domain is a closed interval. So we can note that we can use the Weierstrass theorem because we have a compact domain. Actually, it is closed and there are no holes in the domain. So we have a compact domain, and the function is continuous over the compact domain. So we can use the Weierstrass theorem. At the end of the day, this is a classic constraint maximization problem, and there are 2 steps to take. In step 1, we need to figure out if there is an unconstrained maximum. And in step 2, we need to check the values at the end of the domain 0 and 4. So let's take these steps one by one. Step 1. The leading coefficient is positive, as I have just mentioned, so the only thing we can find is a global minimum, because it is a standard parabolic function. So if the function has a maximum over this closed interval, the function takes the maximum only at the endpoints, or one of the endpoints, or in both endpoints of the interval. So in step 1, we can conclude that we have a global minimum maximum is to be found over 0 or 4, or and 4. We don't know yet. Step 2. We need to check the values at the endpoints. So f0 is -6 and f4 is 34, and this is the maximum. So max over the interval is 34. So once again, proof was based on the Weierstrass theorem. We have a compact domain, which is closed and there are no holes in the domain, and the function is continuous. So all in all, it was problem 1. In the next bunch of problems, we are dealing with a function space, actually a set of functions of which we are supposed to show that this is a function space, a linear space, and with a functional which is interpreted on this set. Okay, so we have function space X with functions in the form ax plus b. And we have a functional over x defined as an integral of the functions over the closed interval 0, 1. Problem A, subproblem A, regards the linearity of the functions in this function space. So we need to check if these functions are linear, and interestingly, they are not. Commonly, we regard these functions as linear because the graph of such functions are linear, but we need to keep in mind that we have a very distinct, very strict definition of linearity in function spaces. So a function is linear if it has this property, and we need to check if the functions in X have this property. So with any real alpha, we need to check if this equality holds. If so, then functions are linear. On the one hand, the left-hand side means that we have this form, and on the one hand we have this form. And there is a difference. We can still have the equality. So we can say that the first form is equal to the second. Okay, these terms, we can drop these terms. So the equality still holds if this equality holds. So we have two options. The equality holds if alpha is 1 or b is 0. So in the first case, a function f is linear if alpha, if and only if alpha is 1. And in the second case, any function is linear to any alpha if b is 0. So please note that if b is 0, then the value of the function is 0, and in this case f is linear. So once again, we can realize that the value of the function is 0 if f is linear. So suppose fx is linear, but b is not 0. In this case, over 0, the value of the function is b. In this case, is alpha b, and this is b. At any real alpha. But if alpha is not 0, then this equality doesn't hold, only if alpha is 1. So if fx is linear, then b must be 0. Okay. We concluded by assuming the exact opposite, and we realized that we received a contradiction if b is not 0, then fx is not linear. Okay, so the condition that over 0 the function must be 0 is sufficient. Is not a sufficient condition of linearity, because we have many non-linear functions to which it holds. So we have many non-linear functions which are 0 over 0. So we conclude that if b is 0, then fx is linear. Okay. In problem B, sub-problem B, what is x? Is it a vector space or what? What are the dimensions? So, first, let's deal with the question, the problem, if x is a vector space. This is a subset of the polynomial functions or continuous functions, but this is only, at this point, we can only say that this is a subset. Even if the set of polynomial functions or continuous functions are function spaces, vector spaces, linear spaces, we cannot conclude yet that set X or subset X is a vector space. To be a vector space, it must have two properties. Please go to pages 11-12 of the Luenberger book, where we can find the properties of vector spaces. So a vector space, a linear space, is close with respect to sums and scalar multiplication. So we need to check if space X, not space, set X has these properties. So we have fx in this form, where coefficient a and b are real numbers, and alpha is a constant, is a real constant. So now alpha times fx can be written as can be written in this form, where most importantly these parameters are real. So set X is closed with respect to scalar multiplication. Okay, this was the first point. So to sum up, we can say if we have a function in set X and if we multiply this with a real scalar, we receive a function which is still in set X. This was the first point to make. The second point, closeness with respect to addition. Closeness with respect to addition. We have two functions, ax plus b and cx plus d. The sum takes the form. The sum is still a function of x, so let's expand the expression. Which can be written in this form. And we can resort to the same argument as above, as a, b, c, d are all real numbers. It follows that a plus c is a real number and b plus d is another real number. So x is close. X is close with respect to addition. So X is a vector space. Hooray! Okay, what are the dimensions? How many dimensions do we have? The simplest way of answering this problem, solving this problem, is to find a basis for X. We have an evident option. So this is a basis. This is a basis of vector space X. Later, in chapters 3 and 5, we will work with so-called orthonormal basis. An orthonormal basis is a set of vectors in which the vectors are of unit length, and each vector is orthogonal to any other vector. But to form an orthonormal basis, we need more tools. First of all, we need a norm with which we can measure the length of a point in a vector space, or the length of a function in a function space, and we need to define inner product with which we can interpret orthogonality. So we need so-called pre-Hilbert spaces in which we will define inner products. Okay, so we say that this basis generates X, or the span of these two vectors is X itself. So we must show that the vectors in this basis is linearly independent to be a basis, to form a basis. We can easily check it. Simply put, none of the vectors, neither 1 nor x, can be linearly combined from the other. So we can say that they seem to be linearly independent. Luenberger suggests a formal test on page 2, not page 2, page 20. So let's go back to page 20 of the Luenberger book. Let's try to combine 0 from these two vectors. Formally, it means that we need to find A and B with the sum that gives 0. So we have this equation if and only if we have this, not equation, equality, if and only if A and B, both E and B, are 0. So they are linearly independent. So 1 and x in the basis. Okay, this is a basis because they are independent. So they do form a basis. The dimensions of the basis is 2, but please note that this is very important. 1 and x is only one possible basis. So we may try to find another basis. So let's try to find one. Let's assume that 3 and x plus 1 is a basis. Is it a basis? We need to check if they are linear. The vectors in this set are linearly independent. So let's try to linearly combine 0 from this basis. So these are the candidate vectors. So let's try to find an A and a B that gives 0 as a linear combination. So we need to solve this equation. We need to solve this equation to any non-zero A and B. We easily realize that this equation holds if and only if A and B, both A and B, are 0. So they are linearly independent. So they form a basis. So we have a basis, a new basis, 3 and x plus 1. How can we combine a function of the form ax plus b from this basis? So let's try to find a way no. Okay, so we have cx plus c plus, okay, and we can see, so this is the basis, and we can see that by choosing c equaling to a, we have completed the first part of the problem. So this part of the problem is solved, but we need to find a c and a d which equals to b. So we know, we use this fact, we use this result. So what we need to solve is b equaling to a plus 3 times c. B is given. So actually, we are looking for a. We are seeking a, and no, sorry, a is given because actually a and b are given, both given. So this is given, this is given, so c is the only problem, and we can express c in terms of b and a, and this is a real number. This must be a real number. So we have the linear combination. So we can use the basis, the new basis, from which we can linearly generate, combine any function of the form ax plus b. So check the result. A x plus 1 plus b minus a over 3 times 3, and this is the basis, and this is the other basis vector, and consequently we have ax plus a plus b minus a, and we can drop these terms, and finally we have ax plus b, which is the desired result. So we can use the basis vectors 3 and x plus 1 to linearly combine a function of the form, any function of the form ax plus b. So the new basis works. It really works. The next problem. Let's find a norm to x, to our function space x. This function space resembles to an everyday Euclidean space, because any point, any function in this space can be described with 2 points, 2 coordinates. So the usual Euclidean is a good candidate. So let's try to use the usual Euclidean norm as a norm on a vector space X. To use this norm as a norm, we need to demonstrate, we need to show that it works as a norm over a function space X. And to show, we need to check if the norm has, to be a norm, it must have three, not two, three properties. One, the norm is 0 only if the only for the 0 function, and it is easy to realize that this equality holds only for A and B is 0. Okay, so conclusion. For the 0 function, the norm is 0, and it is only the 0 function that has 0 norm. All right, second, linearity. This is the second property to be a norm. Let's check this. What does it mean? It means that we multiply both terms in the function with a constant, a real constant, and consequently we have for a function of this form. What is the norm of this function? Let's use the candidate norm squared and alpha b squared, which with direct calculation it leads to this expression, which is the desired result. And the third property, the triangle inequality must hold. As we work with a candidate norm which works in the usual two-dimension Euclidean space, a figure might help. So let me try to represent the basis and the points. So we have a function here. This is ax plus b, and this is coordinate b, and this is coordinate a. And let's have another function here. Actually, they are points in a function space. We have another point in this function space, which is a function. This function is cx plus d. So this is coordinate d, and this is coordinate c. Their sum is somewhere here. This is a function a plus c x, and the other coefficient is b plus d. It really looks as if we were working in the usual everyday Euclidean space. The triangle equality means that the sum, the length of the sum of two vectors cannot be higher than the sum. Once again, so the sum of the length of two vectors, the sum of the length, once again, let me think. The sum of the length of two vectors is at least as high as than the length of the sum of the vectors. Hopefully it's correct. Let me repeat it. So the sum of the length of two vectors is at least as high as the length of the sum of the vectors. Yes, I think it's correct. Okay, so let's use the fact that in the Euclidean space we have the triangle inequality. So in the Euclidean space, the triangle inequality holds. So the length of the sum cannot be higher than the length of the components. Okay, so this is the sum. It has a length, and the length cannot be higher than the length of the component points. This is vector 1, the length, the norm of vector 1, and this is vector 2, and this is the length of vector 2, and this is the sum, and this is the length of the sum. Of the sum of vector 1 and vector 2. So from the fact that in the usual Euclidean space the triangle inequality holds, it follows that the triangle inequality works, the triangle inequality holds in space X. So conclusion: the triangle inequality holds in X too. So conclusion is a norm. All right. So next problem. Let's try to create an isometric isomorphism between X. Isometric isomorphism between X and R squared. how to do this. We have two new concepts, isometric isomorphism. So we need to try to understand these two concepts. So isomorphism is a mapping. We say that a mapping is isomorphic. No, we say that a mapping creates an isomorphism between two sets. So this is the mapping from x to r squared. If the mapping, so T as a mapping, establishes an isomorphism between x and r squared if and only if T has three properties. T must be 1-to-1, 1-to-1, onto, and linear. So in this case we say x and r squared are isomorphic. So if these properties hold, then T establishes an isomorphism between x and r squared. In other words, x and r squared are isomorphic. This is a very important characteristic of two spaces. So isomorphism and isomorphic, they are the new terms in our discussion. So let's check if the mapping T, if we can find a mapping, most importantly, we need to find a mapping which has these three features, these three properties. So let's have the mapping in this form. So what does it mean? If we have a function in this form, ax plus b, on the basis 1 and x, we map, T maps a function of the form ax plus b, which is an element in x, maps into a point a, b in r squared. So actually this is a mapping that maps a function from x into the usual two-dimension Euclidean space. Let's check if T is onto. It is, because for every element in the range of T, which are points in R squared like A and B. So to any for any element in the range of T, the range of T is R squared, we have at least one point, in the domain, which is X. So this is onto. The mapping T is onto. Because if we have a point in R squared, we can go back through T to a function in the form of Ax plus B. And this is unique. This is an additional feature. The point in X is unique. Okay, so yes, T is onto. Second point. T is 1-to-1. 1-to-1. Any X in X, capital X, is mapped into a unique point in R squared, and from any point in R squared, we can go back to a unique point in X. So this is 1-to-1, and so this is 1-to-1. T is 1-to-1, and last but not least, mapping T is linear, which means the following. We need to check if this property holds. This is easy to demonstrate. Starting from X, let's say this is supposed to be F. Okay, plus B beat times TG, and it means that we have 2 points in R squared. So following mapping T, we have left function space X, and now we are in the Euclidean space. We have 2 points in the Euclidean space. These points are A, B, and C, D, and we lengthen these points with 2 constants, alpha and beta, and this is a point in R squared. So what we can conclude, this is a point in R squared, in the 2-dimension Euclidean space, and this point in the 2-dimension Euclidean space implies a function in X which is of the form, of this form. And from this it follows that this equality holds. So we started in X, now we are in R squared, and here we go back to X at this point. So the strategy of the proof was quite simple. We create the point which is in R squared. We check how it looks like in R squared, and we go back. We check if and how we can go back to X. Okay, so to see if there is a mapping that creates or establishes an isomorphism between X and R squared, we need to check if the mapping is one-to-one, onto, and linear. The next step. Isometric. We need an isometric isomorphism. Isometric isomorphism. Which is more than an isomorphism. What does it mean? We need a mapping in which these two norms are equal. So if we calculate the norm of a point in X, we need to check if this point has the same norm as the related point in R squared. So it's no big deal. A function in X takes this form and has the norm which looks exactly like the Euclidean norm in R squared. So this is the first thing to note. Mapping T is a mapping that creates a point in R squared on the basis or from, let's not use this expression, from a function in X. So we have a point, simply put, we have a point in R squared, and we can measure its norm because it is an ordinary point, and in R squared we use the standard Euclidean norm, which are the same. So we use the same norm in both spaces, and the norm of a function in X has the same norm as the related point in R squared. So, conclusion, mapping T establishes an isometric isomorphism. Okay. Now let's turn isometric isomorphism before turning to the next problem. Let's finish this sentence, this conclusion, between X and R squared. And finally, let's turn to the functional in problem D. We have this functional over X as an integral of functions in X over the interval 0 and 1. Okay, let's try to characterize this functional as closely as possible. So, what does this functional mean? So if fx is in the standard form ax plus b, then the functional is simply the definite integral of ax plus b over the interval 0 and 1, and it has a clear value, a over 2 plus b. Is this function linear? Functional, not the function, functional. Is the functional linear? Just as always, we need to check if some properties hold. We need two properties. Alpha times the functional must be equal to the function times this real alpha. This is a transformation of the original function, and the functional over the sum of two functions is the sum of the functional over each function. We need to check if these properties hold. First, it's no big deal, you will see. So this is alpha times the integral. So this is a simple exercise in working with constants and integrals, and we know from elementary calculus that in such a case the constant can be put behind the integral sign. So we have the following function, integral, sorry, and we must realize that alpha can be factored out behind the integral sign, which means we have linearity. Okay, this was one property. The other property. Let's try to calculate the functional for a sum of functions. We use the previous functions, ax plus b plus cx plus d, and we integrate this sum over the interval, closed interval, 0 and 1. It's no big deal. Again, using the integral rules familiar from elementary calculus, we can cut the integral into two halves, so we can integrate the two pieces separately, which means that linearity holds again. So, conclusion, the functional is linear. So this is a linear functional. Next problem, E. Is there a supremum? The short answer to this question is negative. Given the fact that the functional to any function of the form ax plus b is this. So this is the integral of any f, any function f in x. So to find the supremum to this integral means that we can find an a and a b as real constants, real coefficients, to ensure the maximum, to find the maximum, to find a maximum to this functional. But this supremum doesn't exist. So a and b can be arbitrarily high, can be chosen to be arbitrarily high, so we cannot find an upper limit. And in part F, is there an infimum? And for the same reasons, we cannot find an infimum either, because we can choose a and b to be arbitrarily low, so there is no such a thing as an infimum. So this was problem 2. This was quite long. And in the final problem for the day, we will be working with another set of functions, of which we want to show if it is a function space, a linear space, a linear vector space, and another functional interpreted on this set of functions. Let's do the subproblems one by one. And finally, let's turn to problem 3. We have set y as the set of functions of the type ax with a moving over a closed interval, and we have the functional over y is another integral the upper end of the integral is a minus a. So this is another integral, but different from the previous one, from the one we used previously. Part A. We need to check if y is a subspace of x from the previous problem. To be a subspace, y must be a vector space, a linear vector space itself. So the same procedure holds here. We need to check if y has the two basic properties of a vector space. Closeness with respect to addition and scalar multiplication. It's easy to find cases where it becomes obvious that closeness doesn't hold. For instance, let fx be 1x and gx is 1x. even if it is true that f is in y and g is also in y, but their sum is 2x, which is not in y. So set y is not closed with respect to addition. And similarly, if we have fx as x and alpha, say y 5, sorry, then even if f is in y, then alpha times fx is 5x, which is not in y. So set y is not closed with respect to scalar multiplication, so y cannot be a subspace. Is jf, the functional, linear? To be linear, it must have two properties, just like previously. And so let's turn to them one by one. If fx is ax and gx is bx, then f plus g is a plus b times x. And then the sum, the functional of the sum, is a bit tricky. It ranges from 0 to a plus b minus a plus b, and yes, we can factor out. No, we can first, let's cut the integral into two parts. We have ax dx minus a plus, ranging from 0 to a plus b, bx dx minus b. And we can factor out a and b. 0 a plus b x dx minus a plus b factored out 0 a plus b x dx minus b, which leads to, by direct calculation, it leads to this expression. So this is the left-hand side of this equality. So we directly calculated the left-hand side of this equality, and now we can turn to the right-hand side. So the functional at f is simply ax dx minus a, which in a few steps proves to be this expression. So on this basis, the right-hand side of the required equality would be so this is the left-hand side, right-hand side, and it's obvious they are not equal. So the functional cannot be linear, and now we don't need to pay attention to the second part of the definition because it's irrelevant, because the first condition, the first requirement is not met. Okay. Problem B. Problem B. Let's check if there is a supremum exists. From the previous point, it's just a kind reminder. From the previous point, we know that this is the functional value of any function fx, supposing that a comes from this closed interval. Note that at the end of the day, jf, the functional, is the function of a, and a moves in a closed interval. And because of the Weierstrass theorem, there is a minimum and there is a maximum to jf, the functional, because jf, the functional, as the function of a is continuous, and the interval over which a moves, it is compact. So now we need to solve it as an ordinary optimization, maximization, or minimization problem. So let's differentiate jf with respect to a. And now we have this expression, which in the maximum 3 over 2a squared minus 1, which in the maximum is supposed to be 0. So after a few steps we see that we have two possible solutions, from which the first one is negative, so it cannot be a solution, but the other is positive and is in the relevant interval, so this is a relevant solution. The second differential we need to check if it is a maximum or a minimum. This is the second differential. 3a is positive or 0 if a is in the relevant interval. So this is positive or 0, which shows that at this particular value of a, jf has a minimum. Has a minimum, which means that the related function fx is ax. Okay, so we calculate the functional. which is minus 0.5443 or something very close to it. Okay, so we have a minimum, and for the same reason we have a maximum due to the Weierstrass theorem. So to summarize the previous point, min is very close to minus 0.5, where A has the value we have just calculated. Okay, but what about the maximum? Of the functional. Also due to the Weierstrass theorem, the maximum must be at one of the endpoints of the relevant interval of A. So it must be at either a point where A is 0 or when A is 1. So by direct calculation, we receive that the functional is 0 if A is 0, and it is minus 1 over 2 if A is 1. So from this it follows that the maximum of the functional is 0, JF is 0, where the function is 0, because A is 0. And that's all. It was a short problem.